Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I will show CFD parametric study and optimization of a fluid mixing problem. This is a specific processing industry problem. In this problem actually we will be mixing 5 different fluids of different densities and different viscosities and with a different volume. That will be mixed inside a bucket and that will be agitated with the agitator. And finally from this analysis we will try to find out the velocity and pressure inside this bucket. By the same time we'll try to find out the average force and average shear stress on the agitator blades. Next to that, in the parametric study we'll see some input variable. The input variable will be the angular velocity of this agitator. By changing the angular velocity of the agitator we'll try to get all the goals what we have decided. And finally, with the set of parametric goals we will have an idea at what angular velocity what will be the different ranges of our goals. By seeing all those goals and their ranges we'll try to optimize our specific parameter. Okay, so without wasting time, let us start our analysis. Let us check the geometry from here itself whether it is okay or not, right? We have to check the geometry from here and see whether the geometry is okay or not. For checking the geometry, let us select improve geometric handling conditions and check it. It is showing that status is successful, so geometry is okay. Next part you can see whether volume is generated inside or not. It's perfect, so status is successful and we can see a closed complete geometry is generated. So our model is ready for simulation. So we have to start it from flow simulation, and the flow simulation environment will be created with the wizard itself. Let us take the name of the project as project 5. By default it will be taking as project 5. Next to that, unit system. Let us consider the unit system to be SI, and we have to change some unit from here. Pressure will be taken in megapascal and temperature is not an important parameter in this case. Anyway, we'll take temperature to be in degrees Celsius. Excluding that also we have to select some other parameters, like from load and motions we have to select angular velocity should be in the unit of RPM or revolutions per minute. And force we have to select as kilonewton. We have selected all the required units. Next to that, it will be definitely an internal analysis. And from physical features we need to select only gravity and rotation, and the direction of gravity it will be y. So along y direction its value will be minus 9.81 meter per second square, and along z direction it will be 0. And we are selecting rotational effect from physical features. Next to that we have to select liquids. We plan to select 5 different fluids with different viscosities and densities with a different volume, and that will be obtained from user different fluids. We have already selected different fluids like fluid A, B, C, D, E with the different viscosities and different densities. So we are selecting those fluids: liquid A, liquid B, liquid C, liquid D, and liquid E. Next to that we'll consider default wall thermal conditions and roughness, and finally we have to select that thermodynamic parameters. Pressure will be 0.101325 megapascal and temperature will be 20 degrees centigrade. And here in this case, very important part is that is concentration. How much percentage of A, B, C, D, E different volumes will be there? That one should be shown from concentrations. And we know that volume A, it will be 72%. Its concentration will be 0.72. Liquid D its percentage is 3.06%. So concentration will be 0.0306. And liquid C, its volume is 15.94%. So its concentration will be 0.1594. Liquid D will be 2.5%. So its concentration will be 0.025. Finally, liquid E, its concentration is 6.5%. So it will be 0.065. So we have defined the volume of different percentage of fluids A, B, C, D, E. Let us finish this. Now you can see this is the computational domain. Let us hide this domain and we'll go for different boundary conditions. So here in this case, you can see only one fluid subdomain with 5 different fluids. So we need not specify fluid subdomains, right? We can see that one rotating region is created, and to specify a rotating region, we have to do some kind of adjustments. That means we have to select some dummy space or dummy volume inside this bucket, and the dummy space or dummy volume will be completely covering that agitator blades. We have already made one specific volume which is covering almost all the dummy spaces. At this moment we have made that dummy part hidden. So we'll select initial conditions. Initially the dummy space is made up of solid, and from initial conditions we have to make this solid space to be filled up with fluid particles of 5 different viscosities and different densities. So we have to disable that solid component and that to be considered as fluid. Let us select that dummy space from here. This is the dummy space. We have selected that dummy space, and that one we have to disable as solid components. So that dummy space is disabled as solid components, and that will be considered as fluid of 5 different fluids with different percentage volume. You can see here it is. Liquid A is having 72%, liquid B 3.06%, liquid C 15.94%, liquid D 2.5%, and liquid E is having 6.5%. And you can see the thermodynamic parameters also is pressure is 0.10325 megapascal and temperature is 20 degrees centigrade. So dummy space is selected, and that will be considered as fluid with 5 different fluids having different viscosities and different densities. Next to that, we have to specify the rotating regions with some specific angular velocities. Initially, we'll provide an angular velocity of 300 revolutions per minute, and in parametric study, we'll go for different angular velocities. Insert rotating regions, and we have to select that rotating regions from here. The rotating region is selected, and we have to provide the specific angular velocity. Let us provide specific angular velocity to be 300 revolutions per minute. Green check. It is done. Initial condition is provided. Next to that, we have to select some specific goals. We are planning to have 4 different goals. Initially, it will be 2 global goals, and the global goals will be average velocity and pressure inside this bucket. And by the same time, we have to find out some surface goals. In the surface goals, we'll find out average shear stress and average force on the agitator blades. Right? Goals. Insert global goals. It will be average velocity and average total pressure inside this bucket. First one is we are considering average total pressure inside this bucket. Green check. Second global goal, we'll select from here again. Insert global goals, and it will be average velocity inside this bucket. Green check. Done. Next to that, we have to select some surface goals. Let us select surface goals from here, insert surface goals, and we have to find out average force and average shear stress on the agitator blades. Let us select that agitator blades from here. We have selected the surfaces of the agitator blades. Now let us select average force and average shear stress separately. Initially we will select average force, selected, and we can rename this one as average force on agitator blade. It's done. Again we have to select average shear stress on agitator blade, insert surface goals, and it will be average shear stress. We have to see the stability of that agitator blade also. So we are selecting average shear stress. Let us select the surfaces of the agitator blades. It is selected. We want to select only one simple goal, that means average shear stress on the agitator blades. We don't want to create separate goals for each of the different surfaces. That means it will be a single goal of average shear stress on the agitator blade surfaces. Okay, green check, and we can rename this one as average shear stress on agitator blade. It's done. Next to that, we have to provide some meshing. Insert local mesh, and for providing local mesh, we have to select that specific surfaces where we want to have perfect meshing conditions, because we know that better the mesh, better is the solution. Let us select those surfaces and we will provide fine mesh at these specific surfaces. Selected. Now from refining cells, we'll refine this one up to 4 level of refinement, and next to that, from advanced refinement level, we'll make up to 4 level of refinement. Finally, we'll see the display of refinement level, and let us make it up to 4th level of refinement. So refinement is fine enough. Great check. Let us run this simulation. We have already started simulation. With new calculations we are starting. Okay, let us run this one. So we got our results now. Let us see the results from different cut plots, and finally we'll show our results from goal plots also. Initially we'll see our results from different cut plots. Let us see cut plots from here. Insert cut plots. We want to see pressure distribution and velocity distribution from front end, and by the same time we want to see all these things from top plane also. Initially we'll see pressure distribution from front plane. So pressure distribution, you cannot see that much of changes. It is showing almost similar pressure across the front plane. It will be better to see in the form of animation. Let us see pressure distribution from front plane. So we don't see that much of change in pressure, but the pressure range inside this one is very high. You can see pressure range, it is in the range of 0 to 10 megapascal. As we are rotating this agitator with high angular velocity, so pressure generated inside this bucket is very high. Let us clear and hide these things, and we want to see velocity distribution again from front plane. Cut plot, edit definition, and instead of pressure we want to see velocity distribution. So this is the velocity distribution. You can see from the central axis, we can see the velocity distribution along the central line. It is very less. It is in the range of 0 to 0.5 meter per second, and as we are approaching towards the periphery, velocity is increasing, and you can see some kind of impulsive force is generated, and velocity there is very high, which is indicated by yellow color, which is in the range of 3.5 to 4.16 meter per second. Let us see velocity distribution in the form of animation. Now we want to see these things from top plane. So we can change this one orientation and want to see this velocity distribution from top plane. Let us clear and hide these things and want to see velocity distribution from top plane. Edit definition. We want to see velocity distribution from top plane. Green check. Let us see this one in the form of animation. So it is showing clearly that velocity distribution, as it is approaching towards the periphery, its velocity is increasing, but near the central axis its velocity is very less. It is in the range of 0 to 0.594 meter per second, and near the boundary velocity is very high. It is in the range of 3.5 to 4.16 meter per second, and in between we are having velocity in the mid range. It is in the range of 1.78 to 2.37 meter per second. Okay, let us clear and hide. Surface plot also will not be providing that much of variation, because if you see pressure distribution, it will be almost same throughout this bucket, but velocity distribution we have already seen. The surface plot we don't want to see. Next to that, we want to see our flow trajectories. This is very important part. Insert flow trajectories, and we want to see this distribution of different fluid particles inside this bucket. Select other. We want to select the inside surface, and we want to see velocity distribution in the form of arrows and lines. Let the numbers of arrows or lines will be 200. Let us make the numbers to be 100. Green check. The particle study is being generated. It will take some time for getting all these flow particles inside this bucket. So this is particle study. Let us run this one and see how the flow particles are moving inside this bucket. Flow trajectories. Let us play. It will be better to see these flow particles in a different format. Let us clear and hide these things, and we'll see in a different format. You want to see these flow particles in the form of arrows only. Let us play this. We got a homogeneous mixture of 5 different fluids, and it is moving smoothly. It will be better if we see these flow trajectories from top side. It will be better to understand. Let us see these flow particles from top side or top view. It is showing clearly that near the central axis, flow velocity is almost negligible. We don't see any fluid particles near the axis, and all the fluid particles are evenly distributed homogeneously. You can see a homogeneous mixture of different fluids, and near the periphery velocity is in the range of 0 to 0.5 meter per second, and near the surfaces where the flow particles are getting some kind of collision or some kind of impulse is there, in that case velocity is little bit higher, right? Let us clear these things and want to see something else like XY plot and also our goal plots to be checked. Next to that, we want to see XY plot. That means we want to see different parameters with respect to some specific line. We have made only one line from top to bottom. Along this line, it will show different parameters. For that, you have to select that specific line. Then go to that geometry again and select that specific line. This is the line. With respect to this line, you have to check different parameters how it will be moving from top to bottom. We want to see different parameters with respect to this line. XY plot, insert XY plot with respect to this line, and you can select a lot of parameters, but our aim is to see average density of fluid, average pressure, and average velocity. We can check all these parameters from here itself, or we can transfer these things to Excel also. Let us transport all this data to Excel and see across these lines how these parameters will be changing. Here you can see that velocity, initially it was very high, it was in the range of 3.14 meter per second, and as the height is increasing, its velocity is decreasing initially, and again finally for some time its velocity is constant, and finally again it has come down. So finally at the top level velocity is 1.308 meter per second, and at the mid level it was constant for some time. Okay, next to that we will see pressure distribution. Pressure was almost constant, and initially pressure in the range of 3.24 megapascal, and finally the pressure value at the top level it is 3.6 megapascal. So it is showing pressure distribution from bottom to top across a specific line. Next to that, we want to see the density distribution. This constant density of 1134.19 kg per meter cube. Okay. Next one, we want to see our goal plots. Insert goal plots, and we'll transfer all these goal plots to Excel. So the completed assembly data. First one, we'll see average force on the agitator. It is showing that after 239 numbers of iterations, average force on the agitator blade is 57.54 kilonewton. Second one is average shear stress on agitator blade. Initially shear stress was very high, and finally it has come down to 0.957 megapascal. This is very less. It proves that it is quite safe, because average shear stress should be approximately 50% of yield stress. As we have considered material is made up of steel, so its yield stress is 250 megapascal, and the average shear stress should be approximately 50%, or you can say 62.5% of that one. So it is definitely safe. Next one, we'll see average velocity inside this bucket. Average velocity, initially it was very less. It was in the range of 0.2 meter per second, and finally the average velocity after 239 numbers of iterations, it is 1.36 meter per second. And the last one, we'll see average pressure distribution inside this bucket, right? Average pressure distribution, it is showing that initially average pressure was very less, and finally after 239 numbers of iterations, average pressure distribution is clearly understood. Maximum pressure is 2.76 megapascal. Let us close this. Next to that, we want to go for some kind of parametric study. In this parametric study, we have to change the angular velocities, and by changing the angular velocities, we'll see what are the different goals obtained, right? Let us start from here to have different parametric studies. Solve new parametric study. Input variables can be taken from the geometry itself, or can be taken from the boundary conditions. We'll select the input variables from the boundary conditions, and we're planning to take this input variable as the angular velocity. Selected angular velocity as the input variable. This optimization, we have to select here design of experiments and optimization, and we have to select some specific range of input variables. We want to have some specific discrete values of these things. We'll select the values as 250 rpm as the first input variable. Second one will be 450 rpm, and the last one it will be 600 rpm. So with the different rpm of these agitator blades, we'll try to find out our goals. Discrete values have been selected. Next to that, we have to select the output parameters, and those are dependent on goals. In this case, we are planning to select all the goals as the output parameters. Selected, and let us see the scenarios. Scenarios, we have to select three numbers of experiments. Let us create those different experiments. So we have selected three different criteria of experiments. That means three different angular velocities of 250 revolutions per minute, 450 revolutions per minute, and 600 revolutions per minute. With these three different angular velocities, we'll try to find out our different goals, right? Let us run this one and see how the results are coming. Let us run this study. It is done. Now we can see our results from goals. It is showing that when the angular velocity is increasing, all the values are also increasing. When the angular velocity is 250 revolutions per minute, in that case, average pressure is 2.75 megapascal and average velocity is 1.031 meter per second. And average shear stress on agitator blade is 0.87 megapascal and average force on agitator blade is 54.65 kilonewton. When the angular velocity is 450 revolutions per minute, average pressure is 3.53 megapascal and average velocity is 1.99 meter per second. Average shear stress on agitator blade is 1.49 megapascal and average force on agitator blade is 85.036 kilonewton. And finally, when the angular velocity is very high, it is 600 revolutions per minute. In that case, you can find average pressure inside this bucket is 4.85 megapascal and average velocity is 2.579 meter per second and average shear stress on agitator blade is 2.06 megapascal and finally average force on agitator blade is 117.32 kilonewton. From this analysis data, we have some idea that if you want to change any input variable, so what may be the ranges we can select from here. Suppose you want to get the average pressure inside this bucket to be 4 megapascal. So in that case, definitely our angular velocity should be more than 450 revolutions per minute and it will be less than 600 revolutions per minute, right? So next one, we'll go for one goal optimization, and in that goal, our aim should be to have the average pressure inside this bucket should be 4 megapascal, right? So we'll select an optimum goal. Let us start from here. Solve new parametric study, and you want to go for final goal optimization. It will be goal optimization, and in this case we have to depend on input variables again like before. It will be goal optimization and we have to depend on input variables. Definitely it will be rotating regions and we're considering rotating regions as the input variable. That means angular velocity will be input variable. We have to select the range from 450 to 550 revolutions per minute. Selected, and it is dependent on definitely output parameters. Output parameters are dependent on goals. In this case, you have to select only one goal. That means our aim is to find out the average pressure inside this bucket to be 4 megapascal. So we'll select only one goal from here. Selected, and we have to select the target value. Definitely target value should be 4 megapascal. Let us select the target value to be 4 megapascal and we want to obtain this result with a variation of plus minus 0.1 megapascal. Green check. It is done. Let us see the scenario. So maximum numbers of calculations will be 128. In this optimization, initially it will try to get the result with the maximum value. What we have defined, it is 550 revolutions per minute. So with 550 revolutions, it will try to find out the average pressure inside this bucket. Next to that, it will go with the minimum one, that means 450 revolutions per minute. And in this way, it will try to minimize the gap in between and find the optimum value. Okay, let us run this simulation and find our optimum goal. Our goal is optimized. Let us see the goals from here. With 5 design points, we have already achieved our goal. At design point 1, when the angular velocity was 550 revolutions per minute, in that case average pressure inside this bucket was 5 megapascal. In the second design point, when the angular velocity was 450, in that case you can see the average pressure inside this bucket is 3.57 megapascal. At a design point 3, when the angular velocity is 483.50 rpm, then you can see the average pressure inside this bucket is 4.35 megapascal. In design point 4, when the angular velocity is 471.45 revolutions per minute, in that case you can find the average pressure inside this bucket is 3.73 megapascal. And finally, at a design point 5, when the angular velocity is 478.2499 revolutions per minute, in that case we got our average pressure inside this bucket as 4.03 megapascal. So we got our result with a discrepancy of 0.03, which is clearly fine. We achieved our goal plot with an angular velocity of 478.24. So in this way, we can define some different input variables and optimize our results, right? So this is a very simple analysis. This is our today's analysis of CFD parametric study and optimization of a fluid mixing problem. This is a specific processing industry problem. Instead of stopping it here, we can go for further optimization with different input variables, right? If you like to understand CFD in a better way, you can follow my Udemy courses. The link of that one is provided in the description box. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.